go back to the quiz, Q was, what was it, 10,000? P to the minus 2. Check and just make sure that that's right. Is that right? Okay. And I asserted that this minus 2 was the price elasticity demand. The price elasticity demand, we're just changing our notation here. The elasticity of Q comma P is going to be, since Q is a function of just a single variable, we use D. So it's dQdP times P over Q. Now, what is dQdP? Well, dQdP is going to be minus 20,000 times P to the minus 3. But then all of this is just dQdP. It's multiplied by P divided by P. Oops, and I'm left off a 0 here. So this numerator just becomes minus 20,000 P to the minus 2. Notice we add exponents. We've got Q in the denominator. What is Q? By definition, it's 10,000 times P to the minus 2. So you see what happens. This numerator is just twice the denominator. We've got a minus sign, so this is just minus 2. This part right here is divided by that. You're just left with minus 2. Okay. Whenever you have a multiplicative form like this exponent will give you the elasticity. Let's talk about the meaning of this in words. Suppose the price elasticity demand is minus 2. And suppose you want to go home tonight and explain that to your spouse, if you have a spouse or a friend. What did you learn today? Well, one of the things I learned so much, but one of the things I learned was about the elasticity. And then give an example. Okay. Suppose the price elasticity demand for a particular type of beer is minus 2. So what would that mean in words? Suppose the price elasticity demand for, I don't know, say Budweiser beer.
As quantity increases by 1%, price drops by 2%.
Okay, let's just reverse that. What is the independent variable?
No.
Price. Quantity is the dependent. Think of it that way. So then go ahead, Will.
So as price increases by 1%, quantity drops by 2%.
Right. If the price of Budweiser were to increase by 1%, quantity demanded of Budweiser would fall by 2%. So it's a good measure of the sensitivity of demand to price changes. And it's always expressed in percentage changes. And in fact, I don't know, do any of you remember from your introductory economics, in this case, Budweiser would be classified, the demand for Budweiser would be classified in terms of its elasticity as what? Elastic or inelastic?
Sorry, it's elastic.
Elastic. Whenever the absolute value of the elasticity is greater than 1, demand is actually said to be elastic, meaning it's rather sensitive. If the elasticity in absolute value is greater than 1, that indicates a great sensitivity of consumption to price changes. Okay, and the reason this would happen is there are a lot of good substitutes for Budweiser beer. So if Budweiser beer were all of a sudden to jack their prices up 1%, people would switch to another beer. Or take a more dramatic change. Suppose they increase the price by 10%. Quantity demanded would fall by 20%, twice as much. That would be a big fall, big decline in market share for them. Okay. Let me just take one more example. If you look at cigarettes as a group, the price elasticity demand for cigarettes is roughly in the neighborhood of minus 0.4. What would be the interpretation of that?
Increase the price by 10%, and the quantity consumed would fall by 4%.
Exactly right. If you raise the price of cigarettes by 10%, quantity demanded would fall by 4%, less than proportional to the price. Price is going up 10%, quantity is only falling by 4%, less than half as much as the percentage increase in price. In this case, demand for cigarettes would be elastic or inelastic? Inelastic. It's an absolute value is less than one. And there are good reasons for this. If you take cigarettes as a group, okay, for example, if the federal government were to increase the excise tax on all cigarettes, then all cigarettes would rise in price. And maybe by, let's say 10%. If all of this is passed on to consumers, then consumption would fall by 4%. Less than responsive, because cigarettes are addictive. Once you become addicted to cigarettes, very hard to stop. Very hard to stop. So that would explain the lack of sensitivity to price here. Whereas in this case, the quantity demand is pretty sensitive to price changes. Okay, that's the idea of a price elasticity. If we go back to the Cobb-Douglas production function, we could talk about elasticities in this context. And let me give you a specific Cobb-Douglas production function now. Now, can anybody tell me what is the elasticity of output with respect to labor? Yes, 0.7. Because this is a multiplicative form. The exponent on labor is 0.7. So following this rule I told you, the elasticity of output with respect to labor should be 0.7. Now an exam, I wouldn't give you full marks for that answer. But it's good. It's good that you memorize that. Okay, now formally, let's demonstrate that. Formally, what is the elasticity of Q with respect to L? Mathematically, what is that?
Suppose we should start by taking the partial derivative.
Right? It is,
Like L.
yes, it is partial Q, partial L, Zach, times, now the elasticity is not the same as the partial derivative, but it does involve the partial derivative. It's partial Q, partial L times
L over Q.
L over Q. The way to remember this, you know it's always the partial derivative times something. And the way I remember this is that L is down here, so you gotta put it up here. The Q is up here, you put it down here. Or another way of thinking about this is you could say, okay, this is the same as dQ over Q divided by a dL over L, assuming dk is 0. We're assuming that capital is not changing. So you can see it's the proportional change in output over the proportional change in labor, assuming capital is being held constant. Okay. So if you like, you could think of it that way. But what is partial Q, partial L?
70K raised to 0.3.
Right.
L raised to
70K to the 0.3 times L raised to the,
minus 0.3.
very good. Now that is partial Q, partial L. You've got to multiply that by L over Q. And let me put the L here, and let me just put the Q down here. Okay. It's L over Q, but we can move that Q over. Now, look at that numerator. And the numerator simplifies to 70 K to the 3 L to the 0.7. But what is Q? Q by definition is 100 times K to the 0.3 L to the 0.7. So you see the K to the 0.3, L to the 0.7 cancels. And you're left with 70 over 100, or 0.7. So your answer, right off the bat, was correct. But on an exam, I might ask you to demonstrate that more formally. But actually, it's helpful to know this because these multiplicative forms appear fairly often in economics. So if you just look at the exponents, those will give you the elasticities. So in words, what does this mean? What does that mean in words? See, if, I'm always going to ask you this on the exam, because if you know how to get the right numbers, but you don't know what they mean, then that's not enough. So what does this 0.7 mean?
It's labor
Well-
increases by 10%.
Yes.
Quantity will increase by 7%.
7%, yes, exactly right. As Will said, let me back up a second. You could always take a 1% change. So if labor were to increase by 1%, output would increase by 0.7%. Or for a 10% increase in output would increase by 7%. Now sometimes you have to be a little bit careful. Sometimes, in this case it doesn't matter, but because the elasticity is constant, it's always 0.7. But if that elasticity were constant, you'd have to be a little bit careful, and you would need to take a small percentage change in L. Because if you take a big percentage change and the elasticity is not constant, then you wouldn't get the right answer. Okay. But in this case, we're okay, because the elasticity is constant. So if L goes up by 10%, quantity produced goes up by 7%. Now, I won't work it out, but I'll just assert that the elasticity of output with respect to capital is 0.3. And that is, I'll just write it out a little bit. Partial Q, partial K, times K over Q. We work that out, it's 0.3. And what is the meaning of that 0.3?
Capital increases by 1%, quantity increases by 0.3%.
Right. If capital input were to increase by 1%, output would increase by 0.3%.
Would this trick still hold true if 0.3 was 2 instead?
Yes. Then the elasticity would be 2.
Okay.
That would be okay. It's still constant, but it would be 2 rather than 0.3. Then that would mean if capital increased by 1%, output would increase by 2%, twice as much. But in the Cobb-Douglas, those exponents are restricted to be between 0 and 1. So otherwise, you wouldn't have diminishing marginal productivity. then if if the elasticity of output with respect to capital were 2, you know, that would violate the idea of diminishing marginal productivity of capital, which would be kind of bothersome, because we assume that that's a fundamental principle that should be obeyed in the production process. But to give you another example, you might have a demand function that looked like this. Suppose demand, quantity demanded for a particular good, is given by this equation, 100p to the minus 2 times income squared. Let I be income. Let P be the price of the good. Let Q be quantity demanded. Then, what is the price elasticity of demand? Minus 2. If you worked out the elasticity of Q with respect to price, it would just be minus 2. And mathematically, this would be partial Q, partial P, times P over Q. Now, the elasticity of demand with respect to income, which mathematically would be partial Q, partial I, times I over Q, would be what? 2 plus 2. So this would be my example of these elasticity concepts. We've been talking about differentials, and one of the uses of differentials is in this concept of elasticity, which is so important. There are other uses for the concept of differentials. And in particular, let me talk about the total differential. And let's use it in this context. Suppose output is a function of capital labor. Then the total differential of output dQ will just be this. It'll be partial F, partial K dK, plus partial F, partial L dL. This is called the total differential. And the interpretation of this is just the change in output. Now, the change in output will be this term here, partial F, partial K, times the change in capital, plus partial F, partial L, times the change in number. If you take this term all together, that is the change in output due to the change in capital. If you take this term, second term all together, that is the change in output due to the change in labor. So in words, the total change in output is the change in output per unit change in capital times the change in capital, plus the change in output per unit change in labor times the change in labor. Or you could abbreviate this with the total change in output is just the marginal product of labor, marginal product of capital, times the change in capital, plus the marginal product of labor times the change in labor. Now, one application of this idea that occurs in microeconomics is the idea of a production isoquant. Do you remember from studying microeconomics what a production isoquant is?
It's a curve that will produce the same output but with varying inputs of capital and labor.
Yes. When we use this example here, suppose output is a function of two inputs, capital and labor. Only two inputs, okay? Just those two inputs, capital and labor. Then, the isoquant is all the combinations of labor and capital. Let's measure capital on the vertical axis and labor on the horizontal axis. If you take all the different combinations of these two inputs that produce a given level of output, and you map these out on the curve, you might get a nice isoquant that looks something like this. Okay, and this is an isoquant for Q equals Q sub 0. At any point along this isoquant, output is Q sub 0. This curve will have a negative slope because as you use more labor, you need less capital. If you're going to keep output constant, labor and capital are substitutes for each other. You use more labor, then you can use less capital. So if you start off at point A, you're using a lot of capital and a little bit of labor. Now, if you use a little more labor, then you could use less capital and produce the same output. We're assuming the marginal product of labor and the marginal product of capital is always positive. So the curve has to have a negative slope. And if you map out all the points along this curve, that's called a production isoquant. As Jacob said, a production isoquant shows all the different combinations of capital and labor capable of producing a given level of output. Maybe this is an output for, say, 100 tons of steel. You can produce 100 tons of steel using different combinations of capital and labor. If you're at a point up here, say point A, you're using a lot of capital and a little bit of labor. But if you're at a point here, point D, you're using a lot of labor and just a little bit of capital. So there's different combinations of labor and capital that will allow you to produce the same output. Different combinations of the two. Now, mathematically, how is this related to the concept of a total differential? As you move along a given isoquant, this is by the way, this is the isoquant for, say, 100 tons of steel. For 200 tons of steel, the isoquant would be further out. Because if you're producing more steel, you're going to need more capital. So the further out you go, the higher the level of output. Okay, so there will be a whole family of isoquants. But if we move along a given isoquant, along a given isoquant, what is the value of dq?
Zero.
Zero. dq is zero, because by definition, output is the same. So as you move along a given isoquant, the total differential of Q must be zero, by definition of what an isoquant is. But what is dq? Well, dq is just this. It's partial f, partial k, dk, plus partial f, partial l, df. If you set this equal to 0, you could write the following. Partial f, partial k, dk equals minus partial f, partial l, dl. Now, let's multiply this equation by 1 over dl. Then we get partial f, partial k, dl equals minus partial f, partial l. And finally, let's divide both sides of this equation by partial f, partial k. And you get the KDL equals minus partial f, partial l, all over partial f, partial k. And this result is actually useful because the KDL has been calculated holding output constant because we're moving along an isoquant. So what the KDL gives you is the slope of the isoquant at a given point. For example, if you're looking at the slope of this isoquant at this point, say point B, the slope would be the KDL. And the KDL is just minus 1 times the marginal product of labor over the marginal product of capital. Okay, so it allows us to figure out what the slope of the isoquant is at a point. The KDL is just minus partial f, partial L over partial f, partial k. Okay, so we can figure out what the slope of an isoquant is at a given point using this one. So that's one application of the concept of the total differential. One last concept before I let you go for today. There is a concept of a total derivative discussed in chapter 8. Total derivative. And this total derivative comes into play when you have a situation like this. Suppose z is a function of x and y. Okay, we're used to that setup. But in this case, y is also a function of x. So z is a function of x and y, and y is some function g of x. Normally, we think of these two variables as being independent of each other. But suppose in this case, whenever x changes, y changes. In this situation, we have what's called a total derivative of z with respect to x. And the total derivative of z with respect to x, dz dx, is just the following. It's going to be partial z, partial y, times dy dx, plus partial z, partial x. Excuse me, partial z. Yes, that's right, partial z. Wait a second. No, wait a second. Let me start. Let's start this over. Let me show you the easy way to remember this. The easy way to remember this, I'm gonna have to edit this. The easy way to remember this is to first take the total differential. What is dz? dz must be partial f partial x dx plus partial f partial y dy. Now, in this case, see the ultimate source of disturbance is x. And we want dz dx. So just take this total differential, divide both sides by dx. And then what you get is this. dz dx, actually what I was writing in the board a moment ago was right. But I was having a panic feeling that it wasn't right, but now I see that it was. Partial f partial x plus partial f partial y dy. So note, the reason it's called a total derivative is because there are two parts. This is the direct effect of x on z, and this is the indirect effect of x on z. Okay. The direct effect, the indirect effect. I could illustrate this with the channel map. To help you understand this. If we draw a channel map for this problem, it will look like this. Here is z on Earth. Now the value of z depends on x and y. X, let's put x here. X affects y. This is a function right here. And y in turn affects z through the f function. So y in turn affects z. But x also has a direct effect on z, because x is in the f function. So x has this direct effect on z in the f function. Here is the indirect effect. So mathematically, the direct effect is just this, partial f, partial x. The indirect effect is the product of these two terms. Partial f, partial y, times dy dx. That measures the indirect effect. You take the two of them together, you get the total effect. Hence the name total derivative. Here's your total derivative. Let me give you an example of this. Suppose our z function is this. Z is equal to 10x plus x times y. And let's suppose y is equal to 10 plus 2x. So how would you get the total derivative of z with respect to x? Using this approach right here. Well, dz z dx, you can just use this formula. It fits right in there. Notice z is a function of x and y is a function of x. So it fits right into this total derivative formula. So the z dx will just be this. Let me write it again. dz dx is just equal to partial f, partial x, that's the direct effect, plus partial f, partial y, times dy dx. Now in this case, what is partial f, partial x?
10 plus 1.
10 plus y. So you substitute that in here. Put parentheses around that. That's just partial f, partial x. Okay. What is partial f, partial y?
X.
X. Okay. Partial f, partial y is just x. So we put that in for this. And what is dy dx?
2.
2. You've got to go back to this one to get dy dx. And it's just equal to 2. So there you go. And if you want the derivative of z with respect to x, it's just 10 plus y plus 2x. Now, normally what you would do, since you want z, you're differentiating z with respect to x, you would then go back at this last step and substitute back in for y. So it's 10 plus 10 plus 2x. Substituting in for y plus 2x. So you could simplify this, 20 plus 4x. Is the derivative of z with respect to x. That's the total derivative. Capturing both the direct